Welcome one, welcome all. How are you guys today? I'm glad to hear it. I hope you guys are well. I hope this does nothing to change that. It is Tuesday, our second happiest day of the week. This is our first problem session in front of a live studio audience. So I've written a few problems on the board, and we'll try and work through them until people get bored, which is probably one of the benefits of watching this recorded is you can speed it up, and my regular dull droning monotone will just sound monotone but in a chipmunk fashion. So, all right, so let's start with, by the way, all of these problems are going to be variations on a theme. They're all going to involve PV equals nRT. So we have our ideal gas law, PV equals nRT, or we could also go with PV equals N kBT. So let's start with our first problem. We have an insulated container, it's fitted with a piston. That piston contains, or the cylinder contains oxygen initially at a temperature of 20 degrees Celsius, at a pressure of 15 atmosphere, with a volume of 22 liters. The piston is then lowered, which shrinks the volume to a measly 16 liters, and the temperature simultaneously increases to 25 degrees Celsius. So we want to find the resulting pressure. So here we can pick either of these that we want. And if we hold N fixed so that it's constant, R is always constant, then we could argue that PV over T is some constant value. Yay? All right. Then we could say that in this case, P1 V1 over T1 equals P2 V2 over T2. So we have (15 atmosphere times 22 liters divided by our temperature of 20 degrees Celsius, but here we need to be careful, and I'd ask that you write this as Kelvin. In Kelvin, that would be 20 plus 273 is 293 Kelvin. And this should equal, well, I can even simplify this for us a little by saying that this tells us that, what are we looking for here? The resulting pressure, so we want P2. So I can say that it winds up being P1 times V1 over V2 times T2 over T1. Is P2. So I also need to add our V2. So V2 here is 16 liters times T2, which is 25, which we should write as 25 plus our 273 is 298. And let's grab a calculator.
What? Only you?
Yeah.
Oh my god.
So 15 times 22 times 298 divided by 293 divided by 16 is about, give or take, 21 atmosphere.
I was thinking everybody.
We're recording, sorry.
Sorry.
No, okay. Does that make sense?
Yeah.
Makes sense enough.
Yeah.
Okay. So our second problem then is again variation on a theme. Let me make sure the lighting in here is. Let me turn the light on. See if that makes it better or worse. I can't tell whether that's better or worse. So for those of you watching at home, sorry. So in our second problem, we have a weather balloon that here at sea level, at atmosphere, 1 atmosphere, about 76 centimeters of mercury, is inflated to a volume of 3.47 cubic meters and has a temperature of 22 Celsius. We're then going to let this thing lift off. When it gets to a height of 6.5 kilometers, the pressure is now 36 centimeters of mercury. And because the balloon is loosely inflated, the volume of the balloon can actually increase. The temperature is minus 48 Celsius. And so we can follow a similar process to what we did here, right? This time we want to find the volume of the balloon. So if we start from P1 V1 over T1 is equal to P2 V2 over T2. Again, we want to find V2. So we get that V2 is P1 over P2, T2 over T1 times V1. And so let's see, P1 was 76 centimeters of mercury. P2 we said was 36. T2 minus 48 plus 273 in Kelvin over T1 22 plus 273 in Kelvin, and then times V2, or sorry, V1, which was 3.47 cubic meters. So I feel like we've already done this one, but do you have a value or?
5.59.
And this is the approach you took.
Actually, I did. I set up the equation and solved for the amount of moles first. And then,
Oh, that absolutely will work.
Yeah.
Well, let me double check then that
I
I've.
also got a slightly different answer for you for the first one, using that approach. But I think when I converted Celsius to Kelvin on Google, it gave me a different temperature.
That makes sense. So when I take this approach, I get about 5.5 5.87, I'm at around 5.59 cubic meters. Are we okay with this? Susan, is this okay? So this starts again from this idea that PV equals nRT. But if you don't let any moles in or out of the system, then N is constant, R is a constant, and so we should be able to say that P times V divided by T is a constant.
Oh, okay.
And so in that case, P1 times V1 over T1 is equal to P2 times V2 over T2.
Oh, okay. Good, cool.
So then we plug in all the earlier values and all the later values that we know, and we can solve for the one remaining.
Oh, okay, cool.
But it's absolutely true that we could solve for the number of moles, and then plug that in for the second state also. We're happy.
Yeah.
It's okay if I try another one?
Let me finish writing this first.
Well, I'm not going to erase this.
Oh, okay.
That's the beauty of multiple boards.
Oh, yeah, sorry. The old one.
Is I'm going to jump to just a different board. So.
Oh, okay, good.
Okay, so in this problem, we have a car tire that's inflated to a gauge pressure of 24.2. Should I close that?
Yeah, close it. Those close.
Well, okay. They're walking down the hall. A car tire is inflated to a gauge pressure of 24.2 pounds per square inch with a volume of 988 inches cubed and a temperature of minus 2.6 Celsius. After you drive around on it for a while, the volume of the tire expands to 1,020 cubic inches. The temperature of the air inside, which again we're going to pretend is an ideal gas, is 25.6 degrees Celsius, and we want to find the gauge pressure of the tire now. Do you guys remember what gauge pressure means?
No.
I don't know what gauge pressure means.
So gauge pressure is just the reference with respect to atmosphere.
Oh.
So if I
1.7.
tell you that the gauge pressure is 24.2 pounds per square inch, it means that it is 24.2 pounds per square inch above atmospheric pressure, which in pounds per square inch is 14.7. So the actual total pressure here, oh goodness, is this, let's see, 38.9? Did I get that right? Since it's recorded, let's hope I did. And so now what? Well, now it's the same problem we've been doing, right? We want to find the gauge pressure at the end, and so we can say that P1 V1 over T1 is equal to P2 V2 over T2. We want to find P2, so P2 is P1 times V1 over V2 and T2 over T1. But this is absolute pressures, remember, right? So we need to turn this back into a gauge pressure. So after we find P2, we also want to reference this back to a gauge pressure. So we want to take away the atmosphere. Does that make sense? So let's see if we can muster through this. So I already forgot what was P1 here?
38.9.
38.9?
Also, P atmosphere is supposed to say 14.7 pounds per inch squared.
Oh, per inch squared. Bad mark. This is why we need our live studio audience.
I'm there.
What's V1?
988.
Thank you. And then V2 is 1020. oh goodness, 273 plus 20, oh, no, minus 2.6. Oh no, T2. See, it takes so little to fluster me. Kelvin over 273 minus 2.6 degrees. And turn that into Kelvin. So, if we do this, let's see what we get. So 273 plus 25, I should not need a calculator for that. 298.6. That's going to be 270.4. And then times 988 divided by 1020 times 38.9. And I'm getting 41.61, I'll keep an extra sig fig for now, or extra decimal, pounds per square inch. But what we actually want is the gauge pressure. So how do I find the gauge pressure?
You subtract 14.7.
Excellent. So that will be 41 point, I'll just go to 40, oh, we'll keep it for now. Minus 14.7 pounds per square inch. And at least roughly, we get 26.9 pounds per square inch. How's that work? Is that all right for you?
Why we subtract the two pressures?
So remember that the gauge pressure is referenced to atmospheric pressure. And so the gauge pressure is how much above or below the absolute pressure of the gas is referenced to atmospheric pressure.
Oh, okay.
So what we did here is we found that the absolute pressure of the gas is 41.61 pounds per square inch.
Mm-hmm.
But that means that the pressure inside of the tire is 41.61 pounds per square inch, but outside of the tire, the ambient air pressure is 14.7 pounds per square inch. And so the gauge pressure, how much more pressure the tire
Okay.
is this minus this, which is that.
Good.
Does that work for you guys?
Yes.
Okay. So let's try this one. So, and how are we doing on time? I may actually finish earlier than I was worried I wouldn't get through all the questions.
What?
Well, there's one more after this. One more after this is a little harder. Not a lot harder, but a little. Okay, so an air bubble initially sits on the floor of a lake. It has a volume of 19.4 cubic centimeters at the bottom of the lake. And the lake floor is 41.5 meters below the surface. The temperature at the lake floor is also 3.8 Celsius. The bubble then proceeds to rise to the surface where the temperature is 22.6 degrees Celsius. We want to know what is the final volume of the bubble. So can you guys help me strategize a plan here?
We could use find the pressure first, we could use the depth. I don't remember what the equation for that is.
We can use somebody's no, I only know. Like
So up here we have atmospheric pressure, which is 101,300 Pascal. Then down here, the pressure is going to wind up being atmospheric pressure plus rho times G times H, where H is the depth below the surface. So, do you remember the density of water? 1 gram per cubic centimeter or 1,000 kilograms per cubic meter.
1,000.
Yeah. So, so this winds up being 101,300 Pascal plus 1,000 kilograms per cubic meter times 9.81 meters per second squared times, what's the depth? 41.5? Equals,
Wow. 41.5. That's a sea. That's not a lake. Right? 41.5.
it's a Great Lake.
Lake Tahoe.
I'm so glad that that was video recorded. Okay, 9810 times 41.5. I'm getting, let's see, 407,115, and then I have to add 101,300 for a grand total of 508,415 Pascal. Yay? Okay, so now what?
And it's the same as the other equation.
Now it's just like the other problems, right? We have the P1 V1 over T1 equals P2 V2 over T2. And what were we looking for? Volume? So V2 winds up being, let's see, V1 times P1 over P2 times T2 over T1. And there's no reason not to keep this in cubic centimeters. P1 is 508,415. P2 is 101,300. And then T2 was, oh goodness, 22.6 plus 273 is 295.6. Is that right?
I don't know, I'm not really.
Yeah, I think so. And let's see, 276.8. So I'm getting 103.98, so I'm going to round that to 104 cubic cubic centimeters. Yes, no, maybe so?
Yes.
All right.
Yeah.
All variations on a theme. We're somewhat happy. So let's try one more then if you guys don't have
Let
any.
me change that. Oh, we have a lot of whiteboards. Okay.
Whiteboard's all the way down. Okay, so this time I tell you that a sample of argon gas has T equals 35 degrees Celsius, has a pressure of 1.22 atmosphere. I want you to assume that an argon atom is spherical and has a radius of 0.71 angstrom, 10 to the minus 10 meters, angstrom. I then ask what fraction of the container is occupied by atoms. So, can you help me game plan this?
No.
So you want a volume?
I want to know, so you have some box. Doesn't have to be a box, could be a cylinder, I don't care.
Okay.
Could be a sphere, could be whatever you want it to be, I don't care.
Oh, okay.
There is argon gas inside at a temperature of 35 Celsius and a pressure of 1.22 atmosphere. I want to know what fraction of the volume of this box or cylinder or sphere, pyramid, whatever you want it to be, is actually occupied by these spherical atoms. I gave you a hint at the very start. It helps if you have had prior classes with me and you know how lazy I am. The very start of the class, I told you that the ideal gas law PV equals nRT or PV equals NKBT. They're the same equation. Too lazy to have written this if I didn't need to. So let's take that approach.
So this time we should use the second equation, PV equals NKBT. Wow. I understand you.
So what if here, well, what don't I know? Hey, what makes this problem?
Don't know the volume.
I don't know the volume of the container, right?
Yeah.
Yeah.
And so what should I bring over to the other side of this? Well, what if I went with P over KBT is equal to number per volume? Help me sort out what this is. So
What's KB again?
KB is Boltzmann's constant.
Oh. Okay.
So pressure divided by temperature, what's that?
Well, what's the pressure here? So 1.22 times, here, we'll do it this way. 1.22 times 1.013 times 10 to the 5 Pascal.
And what's big N?
Number of particles.
In the
Okay,
diagram.
so we can find the volume of one of the particles. And then, we can relate that to volume.
So if I know the volume of one particle, and I know I have n particles,
Yeah.
then the volume of particles is capital N times the volume of
Yes.
one particle.
Yeah.
What's our temperature here?
308.
350.
Yay-ish. So
What? How do you know it's 308K?
Just add 273.
Oh, okay.
So let's see if I can do this. So I'm getting 2.9. I'm going to keep extra sig figs and or extra decimals here just in the intermediate steps. Yay? And I know on some level this has to be per cubic meter. Right? Because I know the thing on the right is particles per cubic meter. Does that work? So let me make this more explicit. I could say atoms even, right? So now, to Chris's point, we could find the volume of one argon. How do I find the volume of one argon?
4/3 pi r cubed.
4/3 pi r cubed. Yay?
How do we know it's the sphere?
I am asking you to pretend.
Oh, okay.
So,
Would be realistically, it is a sphere, though, isn't it?
it has a
Mhm.
nucleus, and then it has an electron, and you could imagine the distribution of that electron largely spherically symmetric. So,
Can we,
but,
can
you
we
know,
imagine any atoms like a sphere? Like all atoms?
for the most part, that's how we're going to treat
Oh,
them.
okay, good.
So,
Yeah, sphere.
So let's see if we can sort this out. The other thing I could do is, since I know that this is n over v, if I want to find well, let's just carry this through. There's no point in making this harder than it has to be. 0.71 times 10 to the minus 10 raised to the third power times pi times 4 divided by 3, 1.4992, keeping similar number of decimal places, times 10 to the minus 30 cubic meters. And so, so the fraction of volume is the V argon total over V total, but this is also going to be N times V argon over V, right? We already found N over V. So if I take this value and multiply by this value, I get about 4.36 times 10 to the minus 5. Within rounding difference of what I got. I did this earlier today. Questions, comments, concerns?
How do we got V argon total divided by V total?
What we wanted was the fraction of what fraction of the container is actually occupied by atoms. And so that's the total volume of argon atoms divided by the total volume of the container.
Oh.
But as you guys told me earlier, we don't know what the total volume of this container is. I didn't give you that information, right? But I did give you enough information that you could solve for the ratio of N to V.
Oh, okay.
And so we know how many argons there are. And so the total volume of argon is the volume of one argon multiplied by the number of argons.
Oh, yeah. Yeah, cool.
That's all right? There are 2 minutes remaining, so I think I'm gonna stop it here. Coincidentally, I also just ran out of problems that I brought with me today. So, as always, you guys are awesome. Have wonderful days. Thank you for stopping by. Don't be strangers. Enjoy your days, but not so much. We won't see you next time.